In this tutorial, we will see how to work with a single server waiting line model with constant service time. This tutorial builds extensively off the single server exponential service time model, so it is critical that you view that tutorial first. The assumptions for the single server constant service time model are as follows. 1. There is a single server or a team that services a single customer or a single group of customers at a time. 2. There is a single waiting line. 3. Customers are selected based on the arrival time, with the first to arrive being the first to be served. 4. Arrival rates can be described using the Poisson distribution. 5. Service rates are constant. Examples of a constant service rate include an amusement park ride, a car wash, or any service being provided by a machine. 6. There's no practical limit on the size of the waiting line. System utilization rho is computed as the average arrival rate lambda divided by the average service rate mu. The percent idle time I is just 1 minus the utilization. The average number waiting in the queue, L sub q, is lambda squared divided by 2 times mu times the quantity mu minus lambda. L sub s is the average number waiting in the queue combined with the average number waiting in the system, so it is always larger than L sub q. It is L sub q plus lambda divided by mu. The average waiting time in the queue, W sub q, is L sub q divided by lambda. The average time in the system, W sub s, is W sub q plus 1 divided by mu. The probability that the system is idle, meaning no one is waiting and no one is being served, is 1 minus lambda divided by mu. These values are known as the steady-state parameters of the queuing system. In this example, a car wash has an average of 12 customers per hour. Only one type of wash is provided, and it takes exactly 3.5 minutes. Find the steady-state parameters of the car wash. System utilization is lambda of 12 divided by mu of 17.1, or 70%. System idle is just the complement of system utilization, or 30%. The average number in the queue is 12 squared divided by 2 times 17.1 times the quantity of 17.1 minus 12. That works out to 0.82. The average number in the system is 0.82 plus 12 divided by 17.1. That works out to 1.52. The average wait is the L sub q value of 0.82 divided by lambda of 12 for 0.07. This is 0.07 hour. Multiplying by 60 yields 4 minutes. The average time in the system is W sub q of 0.07 plus 1 over lambda of 17.1. This yields 0.13, also expressed in hours. Multiplying by 60 yields 7.58 minutes. The probability that no one is in the system is 1 minus 12 divided by 17.1. That yields 0.30. This is the same as the percent idle calculated earlier. Now here's an example for you to try. The owner of the car wash in example number 1 is considering upgrading the wash to do a better job. Service time would increase from 3.5 minutes to exactly 4.5 minutes as a result of the upgrade. Find the new steady-state parameters of the car wash if this upgrade is made.
Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made.
The 4.5 minute service time means that 13.3 cars can be serviced per hour. System utilization is 90%, yielding a percentage idle of 10%. Average number of customers waiting is 4.05, and the average number of customers in the system is 4.95. The average queue wait is 0.34 hour, or 20 minutes. The average time in the system is 0.41 hour, or almost 25 minutes. The idle probability is 0.10. Is this a change you would recommend? If this video helped you working operations management problems, please consider liking the video and subscribing to the channel.